Hello, ladies and gentlemen. Welcome back to day 6 of chapter 5. We are on 5.3, day 2, the general multiplication rule and tree diagrams. By the end of this lesson, you'll be able to use the general multiplication rule to calculate probabilities. And you'll also be able to use tree diagrams to model a chance process and calculate probabilities involving 2 or more events. As usual, at the end of this lesson, please try this assignment. Let us begin. All right, so we are on 5.3, day 2, general multiplication rule and tree diagrams. And for our first example, one type of rapid COVID test kit claims to have a false positive. A person without COVID receives a positive test result rate of 3.45% and a false negative rate of 0.33%. You can find these details at this website. A false positive test result is one where a person without COVID receives a positive test result. So you know the person doesn't have COVID, but they tested positive anyway. A false negative is one where a person with COVID receives a negative test result. So you know that they have COVID, but their test result was negative. Suppose that 1% of people in a population have COVID and everyone in the population is tested. Randomly select one person from the population. So we need to use a tree diagram to represent this situation. So we're starting out with a randomly chosen person from the population. They have two pathways they can follow. Either they have COVID or they don't. Now set up here that 1% of people in the population have COVID. So that would translate to 0.01. 1 divided by 100 is 0.01. And then 1 minus that gives us 0.99. So 1% have it, 99% do not. Now after these branches, we are going to have conditional probabilities. If you're branching off of the COVID branch, then you already know that they have COVID. That means that that is a condition for following that branch. So the positive and negative test results, this would be if someone has COVID, the likelihood of a positive result versus likelihood of a negative result. And if we know the person has COVID, then getting a negative would be a false negative. They have COVID, but their test result didn't say that. And a false negative rate was 0.33%, so 0.33 divided by 100 is 0.0033. 1 minus that will give us the 0.9967. This should represent 100% of the people who have COVID because this is our conditional probability and these are the only two test results we could have. So 0.33%, and then the rest of the situation, 99.67%, would have positive results. Now, of the people who do not have COVID, if they get a positive test result, that is a false positive because they don't have COVID. That happens 3.45% of the time. That's why we have 0.0345 for our false positive. Now, if they do not have COVID, they test negative, that would be a correct negative test. 1 minus 0.0345 gives you 0.9655. Right, so this is our completed tree diagram. Now, if you randomly select one person from this population, what is the probability that that person tests positive? So we don't care about whether or not they have COVID. We just want to know what's the likelihood that a randomly selected person tests positive. There are two pathways to testing positive. You have COVID and you test positive. You do not have COVID and you test positive. Now, when you're going through the branches of a tree diagram, you multiply the numbers on the branches that connect to each other along the pathway that you want to take. So probability of positive would be the probability of COVID and positive plus the probability of no COVID and positive. 0.01 represents the people who have COVID, and then times that positive test result for the COVID branch would be times 0.9967. That's where these two numbers came from. 99% of the population does not have COVID, but 0.0345 represents the proportion that test positive given that they don't have COVID. Multiply these and you have your intersection. 0.01 times 0.9967 gives you 0.009967. 0.99 times 0.0345 gives you 0.034155. When you add these up, you get 0.044122, which is the probability of getting a positive test result. Now the question that people typically want to know the answer to. Suppose that you randomly select one person who tests positive, so you know the person tested positive. What is the probability that that person actually has COVID? Probability of COVID given positive. We already know they tested positive. Now we want to know the probability of them having COVID given that prior information. And again, following our conditional probability formula, the probability of the intersection, so probability of COVID and positive, divided by the probability of our condition, The thing we already knew was that they tested positive, so divide by probability of positive. Now, we already calculated probability of COVID and positive while calculating the probability of positive. It was this product right here. So the 0.009967 represented probability of COVID and positive, so I'm going to insert that number. The probability of just being positive is what we calculated in part B. That's what I'm going to divide by. If you take 0.009967 divided by 0.044122, you get about 0.2259. So only about 22.59% of people who test positive actually have COVID. And this is something important to consider. Medical tests are often set to a very high level of sensitivity, which means that they're more likely to pop positive than to pop negative, and that allows them to detect when a person has an illness much more consistently. What is the worst case scenario? Having an illness but not catching it in time to actually do something about it, or not having an illness but having a health scare because a test said you had it. This is the reason why doctors' offices always say seek a second opinion or do additional testing. An initial test might have an indicator saying that you might have an illness, but they do further testing because the likelihood of you continually having false positive after false positive after false positive when you don't have the condition is extremely unlikely. One test popping up positive, yeah, it can happen. Multiple tests popping up positive when you don't have the condition, extremely unlikely. But they would rather catch those who have the condition than end up with these false negatives. False negatives and false positives are kind of like squeezing on a balloon. You squeeze one side, the other side has to inflate in order to not pop. Squeeze the other side, you have to release the other one to inflate so that doesn't pop. You try to squeeze both sides and minimize both false test results, and the whole thing explodes in your face. It's just not going to work. So you have to decide which one would you rather have. I personally would rather have a false positive than a false negative because the next test will probably show negative and ease my mind. I would much rather know that I have a condition than not. All right, let's go to our next part of our notes. You can read the following information on pages 365 to 371. Now, what is the general multiplication rule and is it on the formula sheet? So our definition for any random process, the probability that events A and B both occur can be found using the general multiplication rule. So probability of A and B, this is the symbolic notation for that, is equal to the probability of A times the probability of B given A. That's what we were doing along the branches of our tree diagram just now. We were taking the probability of the initial event times the probability of the second event given that the first already happened. Now, if you want to reverse that, if you look at the probability of B, you can multiply that by the probability of A given that B already occurred. Now, this is just restructuring the conditional probability formula that is already available on your formula packet. So while the exact formula is not on the formula sheet, it can be generated. And if you look at this, I have my general formula. And if I multiply by the probability of B on both sides, probability of B cancels from this side, leaving me with the probability of the intersection equal to the probability of B times the probability of A given B, which is what I just generated for you guys. So you're given this formula. You need to do this to generate the multiplication rule, the general multiplication rule that includes conditional probabilities. Now, what is a tree diagram and when is it better to use a tree diagram than a two-way table? So for our definition, a tree diagram shows the sample space of a random process involving multiple stages. The probability of each outcome is shown on the corresponding branch of the tree. Now, all probabilities after the first stage are conditional probabilities. Right, so when events are sequential or conditional probabilities are given, conditional probabilities go on all but the first set of branches, and that's when it's better to use a tree diagram. Two-way tables do not show conditional probabilities. So if you know that you have conditional probabilities, you know that you need to use a tree diagram. A tree diagram is also better when you have more than two sequential events as well. Right, so if you have more than two events, if they're sequential, use a tree diagram. If they are not sequential and you don't have conditional probabilities given, then perhaps use a Venn diagram for it. Right, now in our last example for this lesson, in a 2012 interview with CBS News, Tom Hanks said that 80% of the population are really great caring people who will help you and tell the truth. And I think 20% of the population are crooks and liars. So he split the population into two groups. Truthful people, 80%, liars, 20%. A new lie detector suite, this should have probably an E after it. I will check for more corrections in a bit. So a new lie detector suite has been tested and was shown to correctly identify truthful people 88.9% of the time and correctly identify liars 75.6% of the time. Now, a positive test is one in which a person is identified as a liar, and a negative test is one in which the person is identified as truthful. Sometimes the test suggests that a truthful person is a liar. That would be a false positive. Positive means that they're a liar, but this person was truthful. So truthful person identified as a liar is a false positive, which means that identifying truthful people correctly would be truthful negative 88.9% of the time. Correctly identifying liars would be a correct positive test. So liars positive would be that 75.6% of the time. Right. Other times the test indicates that a liar is being truthful, that would be a false negative. So assume that Tom Hanks and the company that makes the lie detector suite are telling the truth. A randomly selected person from the population tests positive for being a liar. So we already know that they test positive. Find the probability that this person is a liar. We'll get to that in a minute. For now, we're going to set up a tree diagram to help us kind of keep track of all the information. So we randomly select a person, and they're either going to be truthful or a liar. Now, Tom Hanks said that 80% of people are truthful, 20% of people are liars. So we're going to put 0.8 for truthful, 0.2 for liar. Now, of the truthful people, this company says that they're going to correctly identify truthful people 88.9% of the time. Now, a truthful test result would be a negative test result. So if they're correctly identified as truthful, they're going to have a negative result, which means 0.889. 88.9% divided by 100 is 0.889 for a proportion. 1 minus this proportion to get 100% of the truthful people would be 0.111. So that's where I'm getting these numbers from. Now, the liar, if they are correctly identified, they have a positive test. And they're correctly identified 75.6% of the time, so 0.756. 1 minus that to get 100% of the liars. 1 minus 0.756 gives you 0.244. So that would be the setup for my tree diagram. Now on to the calculations. We selected a person from the population that tested positive. So we know they tested positive. Now we want to know the probability that the person was a liar. So probability that the person is a liar, given that we know that they tested positive. That's why this is in this order. Now, based on our conditional probability formula, this would be the probability of liar and a positive test divided by the probability of a positive test. Now, liar and positive test would be going down the liar branch and across the positive test branch, which would be multiplying the 0.2, which is probability of liar, times 0.756, which is the probability of positive test given liar. Right, so 0.2 times 0.756. That's using our general multiplication rule. Right. And then down below, there are two ways to have a positive test. You could be truthful but get a positive test. That's 0.8 times the 0.111. That's this product here. Or you could be a liar and have a positive test, which we were just showing the calculation for, 0.2 times 0.756, which is down here. So if I multiply 0.2 times 0.756, that would give me 0.1512. If I take 0.8 times 0.111 plus 0.2 times 0.756, that combined gives me about 0.24. Divide these two numbers and you get 0.63. That would be about 63% of the time. Now, this is one of the reasons why lie detector tests are rarely used in court, because the probability that a person's a liar given the positive test is only about 63% of the time. So that's not very strong evidence. Okay. Try this assignment and we will see you in class.